Yeah, the screen should be visible, I believe. Yeah, so today is going to be the sixth weekly live session of this NPTEL course of river engineering, brought to you by NPTEL and Swam Initiative. This course has been tutored by Professor Subhashish Datta from the Department of Civil Engineering at IIT Guwahati, and I'm Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research in IISc Bangalore. So far, I have uploaded everything which was discussed in the preceding classes in our YouTube channel. So this is the link for that YouTube channel, and the files relevant to the sessions will also be uploaded at the Google Drive folder. The link for which has already been provided to you guys. So today we will be discussing three distinct questions. Question number three is basically about the scout depth calculation, and question number one and question number two will be about the method of characteristics. Basically, method of characteristics, if you don't know, is basically a method to solve systems. I mean, a system of partial differential equation. So we will be utilizing it to solve, in a way, the Saint-Venant's equations. That is, those are basically the governing equations for fluid flow through an open channel. So we'll be taking up two questions, but before that, I would like to discuss the formulation of those method of characteristics equations. So let me start with that. So far you already know that the Froude number, I've already discussed it in many preceding lectures, is nothing but the flow velocity divided by square root of GD, where D is the hydraulic mean depth, and D also happens to be A by T. So this will be nothing but square root of G A by T in the denominator, where A, capital A, happens to be the cross sectional area, and capital T happens to be the top width of the cross section. So this also can be written as the flow velocity divided by c, where c is something known as the celerity. So celerity is nothing but the denominator of the Froude's number. So if you happen to throw a stone in a water body, let me just check whether I actually started recording or not. Yeah, I did. So if you happen to throw a stone in a water body, some sort of waves will be produced in it. So the velocity of disturbance of the flow created in a channel is what we call as the celerity, and it is denoted as c, and c is nothing but, which is the denominator of the Froude's number. C is nothing but g a by t, square root of. So now let us suppose there is a flow velocity v, and you create a disturbance to it. How? You may actually throw a stone into that water body. You create a disturbance to it. So we will get two cases. Case 1 will be that V is greater than C, that is the velocity of the flow is greater than the velocity of the disturbance, or velocity of the flow is less than the velocity of the disturbance, or the celerity. So there may be two cases. Let me take it to the next slide. Okay, so case 1 is basically, let us suppose a case where the velocity of flow is much greater than that of the celerity. Celerity happens to be the denominator of the Froude's number. So naturally, the flow would be supercritical because the Froude's number would be much greater than 1. Yeah, where in case I didn't explain it earlier, V is nothing but the flow velocity. So what would happen in this case? This we know that for this case, Froude's number would be greater than 1, and it is a supercritical flow condition. So what would happen is that the disturbance will flow in the direction of the flow, because the flow velocity itself is so large that the disturbance itself will not be able to create a distinct impact. So V minus C will be the net resultant moment created, and it will be in the direction of the flow, means from upstream to downstream. So let us suppose we take a counter case. The first case was V being much greater than C. Let us suppose we take the opposite case. V is much lesser than C. So, so for this case, the disturbance may flow in direction of the flow. V is much lesser than C, so we know that Froude's number would be lesser than 1 and it will be a subcritical flow condition. So the net resultant movement in this case, what's from left to right, if we suppose that the upstream side is left and the downstream side is right, so the net resultant movement in the first case would be from left to right, whereas in this case the net resultant movement will be C minus V, and it will be in the upstream direction. That is from right to left. In case the upstream is left and the downstream is right, so it will be exactly opposite. These two cases will follow very different situations. So let me just conclude it in the next slide. So the conclusion out of it is that in open channel flow, a small disturbance, which is nothing but the celerity, can propagate upstream and downstream. We already showed the two cases where the propagation can be upstream or downstream. So let us suppose an observer is sitting on the or standing on the bank of the river. So what will you observe? For an observer standing on the bank, the absolute speed of the small wave. So this term wave itself is a huge term. I will be explaining it about wave in 20 minutes from now. So the speed of the wave happens to be v plus c and v minus c, where v equal to the velocity of the flow. Now v plus c and v minus c are very important. These are what we will term as the C1 characteristic and the C2 characteristic. I will explain it in from the next slide. So let us suppose we differentiate. We are basically trying to, the objective from now onward will be to try to simplify the Saint Venant's equation so that it is represented by some set of uh, ordinary differential equation. You know that the Saint Venant's equation is basically two different partial differential equation. We want to simplify it into four different ordinary differential equation, and that is how we will come at the method of statistics. So the first exercise is to differentiate celerity with respect to time and space. So del by del t of celerity square, we are trying to differentiate celerity. So we are taking c square because, I mean, if we differentiate c square rather than c, we will get a very well-known expression. So this is nothing but 2c del c by del t. So this can be represented as g del d by del t, since c is nothing but square root of gd for a rectangular open channel where d is the depth of the flow. Let us suppose we term this equation as number 1. Now differentiating celerity with respect to position, that is x, we get another expression del c by del x, which can be simplified to g del d by del x. This is the second equation. Just recall that the Saint-Venant equations, which by which I actually ended the previous live weekly session, the Saint-Venant equations was a set of two different partial differential equations. So they could be written as, in terms of depth of flow, del d by del t, a by t del v by del x plus v del d by del x plus v by b, where b is the width of the flow, del a by del x, where a is the cross sectional area, where d is constant, equal to 0. So this is the first equation, which is the conservation of mass or the continuity equation. And central equation we also know is a combination of continuity equation and the momentum equation. So let us now write the momentum equation: del v by del x plus g del d by del x plus g sf minus s naught equal to 0. So these are the two Saint-Venant's equations. SF and S naught are the friction slope and the bed slope. Apart from that, A and B are the cross-sectional area and width of flow and top width of flow or the open channel. D is equal to the depth of flow. So this is the fundamental Saint-Venant's equation or the SV equation. Okay, so we want to basically replace these two partial differential equations with four different ordinary differential equations, and that is how we arrive at the method of characteristics. So let us just try that now. So the first thing is to replace del d by del t and del d by del x terms from equations 1 and 2 in the Saint-Venant's equation. So we get 2 del c by del t plus 2v del c by del x plus c del v by del x equal to 0. Let us term it as equation number 3. In case you are getting bored, I mean, please hold on, because in a few moments from now we will arrive at a very simple expression. Del v by del t plus 2c del c by del x plus v del v by del x plus g sf minus s naught equal to 0, number 4. So the first expression would be to take 3 plus 4, equation 3 plus equation 4. What do we arrive at? We arrived at del by del t plus v plus c. Del by del t is an operator. Del by del x v plus 2c plus g sf minus s naught is 0. Let us term it as equation number 5. And 3 minus 4, and simplifying we get another expression, del by del t plus v minus c The thing is that this equation will yield us the exact same thing, but the pluses will become minus. Del by del x v minus 2c plus g sf minus s naught is 0. Let us term it as equation 6. Let us take another slide. So let us write equations 5 and 6 as this. Capital D by dt times v plus 2c equal to minus g sf minus s naught. This is, let us suppose, a1, equation a1, and d by dt v minus 2c equal to minus g sf minus s naught. Let us suppose this is equation b1. Okay, so capital D by dt is nothing but the absolute differential. I will explain it in the next slide. Why are we representing it like this? It is the absolute differential, and a1 is nothing but the forward characteristic, and a2 is the backward characteristic. So these two equations, fundamental equations a1 and b1, are basically along their trajectories, along their characteristic trajectories. Dx by dt is equal to v plus c. For corresponding to equation a1, we will term this equation as equation a2. This is the forward characteristic. Let us suppose we term it as c1, and dx by dt for equation b1, the trajectory would be v minus c. This, we, let us suppose we term it as b2, and this would be the backward characteristic trajectory, c2. So we get set of four different ordinary differential equations to replace the conventionally used Saint-Venant's equation, and this will become very essential in solving a few problems. So at this stage we can just memorize these four expressions, and the difference is that you just need to memorize one expression, this, and then just replace the pluses between v and c into minuses to get the backward characteristic from the forward characteristic. So far, the thing which we did was that we arrived from these set of Saint-Venant's equations, two, which are two in number. These two are partial differential equations, to these set of four different ordinary differential equations as per the method of statistics. Someone may be wondering, why are we, I mean, increasing the number? Won't it increase the computation time? No, actually the thing is that solving a partial differential equation is much tougher than solving more number of ordinary differential equations. So we took the easier route of converting two different partial differential equations into four different ordinary differential equations. So these four equations happen to be the replacement of Saint-Venant equations in method of characteristics. So for observer traveling along forward characteristics, equation A1 and A2 are valid at any point, and for an observer which who travels along the backward characteristics, then equation B1 and B2 are valid at any point. So with this, I will depict the graphical representation of the method of characteristics. It is in the next slide. So let us suppose we show it in an xt plane. where x is in the x-axis and t means the time is in the y-axis. We take two different conditions. One is of subcritical flow, the other of supercritical flow. Okay, so the first case is subcritical flow. How do we plot the characteristic equations? The other one will be supercritical flow. Okay, so let me show it like this. So the forward characteristic will look somewhat like this. Forward characteristic, if you remember well, is nothing but this. The first equation A1, d by dt of v plus 2c is equal to minus g sf minus s naught. And the backward characteristic for a subcritical flow condition would look like this. Backward characteristic. So the forward characteristic will have a slope, and that slope dx by dt we know is nothing but v plus c. This is nothing but equation A2. And similarly, the backward characteristic also has a slope dx by dt equal to v minus c. And this is the point of intersection. This will be very essential. So this is a subcritical flow. So the flow can be moving forward as well as backward in a subcritical flow condition. What about supercritical flow condition? Since the flow velocity is much larger than that of the salinity, so both the backward and the forward characteristics tend to follow the direction of the flow path. So this would be the forward characteristic, and this in the dotted part would be the backward characteristic. The slope for backward is v plus c, and for forward is v minus c for a supercritical flow condition. So, so this is how the characteristics would look like for. I mean, the plots for characteristics would look like for an open channel flow following the method of characteristics. Now I will come back to the expression d by dt, which I termed as the absolute differential. I will explain how we arrived from equation number 5 and 6 to equation numbers A1 and B1. Let's check it out. So the absolute differential d by dt of a scalar function phi, which is a function of x comma t, would look like d phi by dt, the capital D. Okay, so it is nothing but del phi by del t, means a partial derivative of the scalar function with respect to time, plus del x by del t del phi by del x, and this term is nothing but the velocity. So this would be d phi by dt is equal to del phi by del t plus v del phi by del x, and it would be along a characteristic trajectory dx by dt equal to v plus minus c, plus for the forward characteristics and minus for the negative or the backward characteristic. Let us take another case out of it. So from this we basically arrived from the Saint Bernard's equation uh, to the four very interesting method of characteristics equation for an open channel. Okay, so for a horizontal frictionless channel, the characteristic system of equations become v plus 2c is constant. How? The thing is that it's horizontal. So horizontal, it means that the bed slope is zero. Frictionless means the friction slope is also zero. So SF minus S naught, that term will cease to exist. This right hand side term on the A1 equation as well as the B1 equation will be zero. So d by dt of v plus 2c will be 0. So what do we get if the differential of something is equal to 0? This means that something is a constant. So that is why we get v plus 2c and v minus 2c as constants. So v plus 2c is constant along C1 characteristic. This is nothing but d by dt v plus 2c is equal to minus g s naught minus sf. This is 0 and d by dt of v plus 2c is equal to 0. So this is nothing but v plus 2c is equal to constant. So this is how it is arrived at. And the second term will be along the C2 characteristic, it will be v minus 2c being constant along C2 characteristic. So if the term g s naught minus sf is constant along the channel and independent of time, if g s naught minus sf is constant along channel and independent of time, then we get, this is the second case. This was the first case, which is a much simpler one. Now, if it is uh, constant but independent of time, so we can take that out, take that term inside the d by dt expression because it's independent of time. Sf minus s naught times t along C1 characteristic and d by dt times v minus 2c plus g sf minus s naught times t equal to 0 along C2 characteristic. So these are the two cases which we may get from the method of characteristics. The first case is just cancelling out the right hand term expression, and the second case is the one in which we assume that the right hand term expression, that is g times s naught minus sf, exists, but it is independent of time. Why? So that we can enter it into the differential d by dt, but it's also constant. Okay, so in order to enter it into the differential, we need to again multiply this with t, because the differential d by dt of g sf minus s naught into t will be nothing but g sf minus s naught. So that is why we multiplied it with t in both the equations which we saw right now. Okay, let's move to the next question, the next part. Okay, so we get that from this, we get that d by dt. Let us suppose we just see the first equation. We get d by dt v plus 2c plus g sf minus s naught times t equal to 0. So what do we get? We get that whatever is inside the expression is nothing but constant along the C1 characteristic, because dy dt of something is 0 means something is something has to be constant. The funda is that if dy dt of something is 0, this implies something is a constant. So that is what we are going to do here. This thing, I mean, whatever is inside the brackets will be a constant because its derivative, time derivative, is nothing but 0. So this implies v plus 2c plus g sf minus s naught times t is constant along C1, that is for forward or C1 characteristic, and v minus 2c plus g sf minus s naught times t is constant along the backward characteristic, that is C2. This is these are the two inferences which we get from it so far. So let us quickly skip into the first problem, which is an application of whatever we discussed so far. Consider an infinitely long channel. Flow measurements at two measurement stations are given at t equal to 0. Calculate the location, time, and flow properties at the intersection of the characteristics issuing from the two measurement stations. We are assuming that SF equal to S naught equal to 0. That is case number 1, which we just discussed now. Okay. So the Saint Venant's equation becomes d by dt v plus 2c equal to minus g sf minus s naught, and sf and s naught has been equated to 0, so we can straight away say that this is 0. This is the forward characteristic, and we get the backward characteristic equation as v minus 2c equal to minus g sf minus s naught, and sf and s naught are equal to 0, so this will again be 0, and so this is the one corresponding to the backward characteristic. Along the trajectories, dx by dt equal to v plus c for C1, and dx by dt equal to v minus c for C2. Okay, now we need to put in the values from the tables given here. Let us just do it in the next slide. At t equal to 0, the basic flow properties are okay. So let us suppose we write for station A, we have to tabulate it, and for station B. So the distance x in kilometer was 1.5 kilometers and 4.2 kilometers from the table which has been given in the form. This was 1.5 and this is 4.5. C, that is the celerity in meter per second, would be equal to 9.81 into 0.65. The depth of the flow is 0.65 given in the uh, uh, row number 2 of this table. So it will be 2.52 meter per second. Similarly, for station number B, it will be square root of g times d, that is 9.81 times 0.73. 0.73 comes from row number 2, this expression, and this will be nothing but 2.67. Now V plus C in meter per second would be plus 2.73 plus 2.89. So it's very simple. V is given 0.21 plus the celerity you are doing, and V is given for A, station A, as well as V is given for station B. We're just summing it up. Similarly, we need to find V minus C as per the method of characteristics. So that would be minus 2.31 and minus 2.54. Then V plus 2C, which is the term under d by dt. In meter per second, it would be plus 5.26 plus 5.57. V minus 2C in meter per second will be minus 4.84 meter per second and minus 5.13 meter per second. So we have to assume, number one, assume that the characteristic lines are straight because no other information is given in the problem. Lines are straight. Ideally, they have to be curved like the ones I showed in this slide, but we are assuming that they are straight so that we can know the intersection and we can find the results. So what do we get then? Let us see. Slide. So the forward characteristic issuing from station A would be x at A plus 2.73 times t. 2.73 is nothing but the velocity, that is v plus c for the forward characteristic. Forward characteristic issuing from station A. Similarly, x will be equal to xb minus 2.54 times t. 2.54 was for station B, the v minus c term. Why minus? Because we are assuming that movement from left to right will be positive. Hence, this minus is coming up. So, why these sign conventions are required? Sign conventions are required to, uh, I mean, be in coherence with your calculations. Otherwise, it will be a big issue. You will observe this in probably the second part of weekly live session 4, which I covered 2 to 3 weeks back. So in the very end, we solved a question for hydraulic hydraulic jump. So we in that question also we chose a very common Cartesian coordinate system just to ensure that all the calculations which we are doing are constant. So this is the backward characteristic from station B. We need to know where the characteristics intersect, which I termed as the point X in the original the point X in the original diagrams. So we find that the characteristics intersect at x equal to 2.90 kilometer for t is equal to 512 seconds, and the flow properties at intersection should satisfy two different equations, v plus 2c, which will be for station A va plus 2ca, for forward characteristic equation,
from station A, and V minus 2C is equal to VB minus 2CB, which is the backward along the backward characteristic issued from station B. So solving these two equations, we finally get that, out of these constants, we get that V is nothing but 0.065 meter per second, and C, that is a celerity, happens to be 2.60 meter per second. So corresponding to it, D, C is equal to square root of GD, so D will be 0.69 meters. So we got as 0.065 meter per second. C is equal to 2.60 meter per second. This implies D will be from C is equal to square root of GD. D will be 0.69 meters at intersection of the two characteristics issuing from the two measuring stations, assuming the friction slope is equal to the bed slope equal to 0. So this is how we arrive at this. Okay, so I will just give a brief background of whatever we covered so far with the method of statistics, so that it doesn't become very boring. Uh, Yeah, so these are the two set of Saint Bernard's equation which we tried to convert from a series of two partial differential equations to a series of four different ordinary differential equations, which happen to be these equations. Yeah, so these are the four different ordinary differential equations which we converted from the Saint Bernard's equation. So these four equations also represent the Saint Bernard's equations itself. Okay, now let us take the four distinct features of any method of characteristic equations, and let us try to plot them. So how would the plots look like? So we solved this equation. Let's move into, before jumping into the equation a question which was asked in the assignment number 4, we will try to solve something else, understand something else, the patterns of the characteristics. Okay, so the characteristics are V plus 2C equal to minus G SF minus S naught. This is the forward characteristic. D by dt, just convert this plus into minus, equal to minus G SF minus S naught. This is the backward characteristic. So this is a system of four different ODEs. ODEs means ordinary differential equations along d by dx by dt equal to v plus c along forward characteristic, which we are terming as c1, and dx by dt equal to v minus c along the backward characteristic, which we are terming as c2. So the slope of the characteristics will be dt by dx of the characteristics in a t versus x planes characteristics. Let us suppose that is delta 1 will be dt by dx. Dt by dx is nothing but 1 by v plus c for a forward characteristic, so it will be 1 by v plus c along forward C1 characteristic. We are just arriving here to here. So, and tan delta 2 is equal to dt by dx is equal to 1 by v minus c along backward or C2 characteristic. So we arrive at the slopes of the characteristic curves. Now let us see how they would look like uh, on graphically. Yeah. So we again take four different formulations for the t versus x plane. This is the forward characteristic C1. The dotted one is the backward characteristic C2. E1 happens to be the intersection. This is delta 2, which is the slope of the backward characteristic. This is delta 1, slope of the forward characteristic. So this is a case of subcritical flow, which I showed in the previous like 10 slides from now also. Let us take another case where it is a critical flow. So at critical flow, the backward characteristic will be just vertical to the tx plane. Forward characteristic would look like this. Backward characteristic C2 will be vertical. So delta 2 will be pi by 2 because it's 90 degree. And this is delta 1. Critical flow condition where Froude number is equal to 1. Let us take a third condition of supercritical flow. C1 would look like this. Someone present. No, I think no one was trying to enter. And C2 will look like this. Let this be E1, the point of intersection. E1 point of intersection. So this will be how the supercritical flow condition would look like in a characteristic plane. Supercritical flow, Froude number is greater than 1. So we chose to understand uh, three different patterns to three different cases for a subcritical flow, a critical flow, and a supercritical flow, and we plotted them graphically just to understand how they would look like. Let's now jump into the simple wave equation because the next question is actually about a positive surge. So for that, I would like to just introduce what a simple wave actually means. So a simple wave problem, it is nothing but just taking the bed slope is equal to the friction slope equal to 0. So the same equations apply. We are just neglecting or cancelling out the equations on the right hand side on the method of characteristics. So the method of characteristic would look like V plus 2C equal to 0 along forward characteristic and d by dt V minus 2C equal to 0, which is the backward characteristic, and the trajectories will be along dx by dt equal to V plus C for the forward characteristic and dx by dt equal to V minus C for the backward characteristic. So we just get that V plus 2C equal to constant along forward characteristic for a simple wave, and v minus 2c equal to constant along backward characteristic for a simple view. Now let us understand what surges actually mean. What are positive surge? What are negative surge? So positive surge is a condition in which the wave is induced by a rise in water depth. I will explain it using figures. And a negative surge is the one in which wave is induced by a drop in water depth. I will take a case of a positive surge to explain how we arrive at the final formulations. Let us. So for making the figures, I will take another slide. So let us suppose we are taking a case of fully developed positive surge. Let us suppose there was a gate. We just drop the gate suddenly. So an unsteady flow condition will start. So this will result in a positive surge like this. This is the free surface level. This was the dotted one was the initial height of the or the depth of the flow. Depth due to the surge is capital D. The flow velocity is moving from right to left in our case. The initial depth of the flow was d naught, okay, and the initial flow velocity was v naught in our case, and surge speed is u, capital U. So this is a positive surge as seen by an observer standing on the bank of the river, okay. So this is the gate being uh, gate closure happening, due to which this positive surge actually started. So this dotted one was the initial water level. So let us just try to convert this figure into something simpler. So this is nothing but we are trying to make it a quasi steady flow. This is an unsteady flow, but to apply the fundamental continuity equation and the momentum principle, we need to convert it into a quasi steady flow. So this is a quasi steady flow analogy. We just take the control sections towards the corners of the figures to convert it into this. And for this problem, if you are having any issue, then please go through the weekly live session part 2, last question of the weekly live session 3 part 2 live question. I have explained it very decently in that YouTube video. So this is as seen by an observer traveling at surge velocity. Surge velocity. So if we do that, then yeah. So this was the initial depth of the flow. This was the final depth of the flow due to the positive surge. So this is just the relative velocity formulation. So the velocity of the flow here would be v plus u. The surge speed is basically added up, and the flow here would be v naught plus u where the surge speed is nothing but u. So we try to write a set of two different equations, the continuity equation and the momentum equation for it. So the continuity equation is nothing but v naught equal to v plus u times d, the continuity equation, and the momentum equation is, if you are having problem in this, please go back to lecture 3 part 2 last question. That will solve everything. I mean, how to take the control section and everything. So the same control section has been taken here. This is the momentum equation. So the subscript O here, the subscript O, whichever expression has subscript O, they are basically the initial flow condition, and the variables are D naught, D, V naught, V, and U. And we know some expressions already. We know V naught already because it's the initial flow. We know D naught already, which is the initial depth of the flow. We also know Q naught. Q naught is the initial discharge. So we know that in case of total closure of the gate, the Q naught will be 0 because of the complete closure of the gate. So out of the variables given here, we already know a few of them. It's not like we don't know all of them in our formulations. So the continuity and the momentum equation, if you combine them, they will yield these two equations: d by d naught equal to half square root of 1 plus 8 fr naught square, means the initial Froude number, minus 1, and the Froude number at some point of time will be 2 to the power 3 by 2 fr naught. By solving these two equations, the continuity and the momentum equations, by square root of 1 plus 8 fr1 square minus 1 power 3 by 2. So where the surge Froude number fr naught is the surge Froude number will be v naught plus u by square root of gd naught. Why did it become v naught plus u? Because we are having an observer who is moving at a surge velocity. That is why v naught and u are being added up. This is nothing but the relative motion formulation. So we try to convert an unsteady flow problem into a quasi steady flow by becoming an observer who is traveling exactly at the surge velocity. That is why the surge speed gets added up to both the flow velocities. That is the initial flow velocity and the final flow velocity because of the positive surge formulation. And Fr will be V plus U square root of GD. So we get these two formulations. Now let us see the equation, the problem which we actually wanted to solve and how to solve them. We finally arrive at it. Yeah. At the opening of a lock into a navigation canal of negligible flow, water flows into the canal with a linear increase between 0 and 30 seconds and a linear decrease between 30 and 60 seconds. In the navigation canal, the water is initially at rest. The initial water depth is 1.8 meter and the canal width is 22 meter. Calculate the characteristics of the positive surge and its position with time. Okay, so let us just first of all tabulate it, whatever we get, the time in second and the discharge in meter cube per second, which is provided. At 0, the discharge is 0. 0 to 30, it is increasing linearly. So it would be 15. and linear decrease between 30 and 16. So at 60 it would be 0 again. Step 1 of the formulation is that the to find the initial conditions. The initial condition given here is that the velocity of the flow is 0, already given in the problem, and the initial celerity will come from square root of gt, which will be 4.2 meter per second, coming from square root of gd naught. Okay. Then step 2 is the initial forward characteristic. So for that we need to know the timing, that is x by the celerity 4.2 meter per second, where x equal to 0 at the water lock and x is positive in the downstream direction. We are already choosing a sign convention towards the navigation canal. So let's take another case. So the discharge at x equal to 0 and the time t naught, it would be the velocity times the area. Area is the depth of the flow times the width of the banks. Width is w. This is the continuity equation. So v x comma 0 t naught from the method of characteristics will become v naught plus 2 c at x equal to 0 t naught minus c naught. This comes from the same formulation of choosing the surge velocity as the observer velocity. C x equal to 0 is can be calculated as g times d, depth of the flow at x equal to 0. So let us just tabulate it. T naught in seconds, C x equal to 0, T naught in meter per second, and V x equal to 0, T naught in meter per second. Let us take gap of 5, the time interval as 5. Okay, so for 0 it will come as 1.8 from this expression. The velocity will be 4.2 from this expression. 5 it will be 4.23 and 0.06. For 10 seconds it will be 4.26 and 0.12. Moving on, we will finally get for 60 seconds the celerity will be 4.20 and the velocity will again be 0, which basically satisfies our problem. So they wanted the characteristics of the and the position with time. The position with time and the characteristics are available. Now let us move to the last question of our weekly live session. This is a question about the scout depth again, which comes very prominently among the assignment problems. Uh, a bridge on an alluvial stream has the features of the design state. Upstream depth of flow is equal to 3.5 meters. Discharge intensity equal to 10.5 meter cube per second per meter. Bed condition equal to plain bed. Bed material is median size. D50 is equal to 1.0 mm. Uh, Piers are round nosed, 12.0 meter long and 1.5 meter wide. Estimate the maximum depth of scour at the bridge piers when the angle of the attack of flow with respect to the pier front end is 0 meters. Okay, so for this, the scour depth has been given. I mean, it's an empirical formulation. So the formulation happens to be like this: k1 k 2 times k1 k2 k3 k4 a to the power 0.65, y1 to the power 0.35, Froude number fr1 to the power 0.43. Now k1, k2, k3 and k4 are the correction factors. A is the width of the bank, width of the river, y is the depth of the flow, and fr happens to be the Froude number. So let us see. K1 is the correction factor for pier, nose shaped pier. From the table given in the video will be 1.0. K2 is cos theta plus L by A sin theta to the power 0.65. Already theta is given as 0 degree. Okay. Angle of attack with respect to the pier front end is 0. So theta is 0. So this implies sin theta term will be 0. L by A times 0 will be 0. So cos theta is 1. 1 to the power 0.65 is 1. So K2 will be 1. K3 is correction factor for bed condition. For plain bed in our case, from table will come out to be 1.1, and K4 is a correction factor for armoring by bed material for D50 mean dia less than 2.0 mm, which will be 1. Okay, so the approach Froude velocity, Froude number is V1, the flow velocity, times G times H1. H is the depth of the flow. So V1 is 10.5, which is small q, discharge per unit width, by 3.5 by square root of 9.81 times 3.5, which comes out to be 0.512, the Froude number. So Ys is equal to 2 K1, K2, K3, K4, a to the power 0.65, y1 to the power 0.35, fr1 to the power 0.43. You need to memorize these equations, unfortunately, because the course moving into the sediment hydraulics part becomes extremely empirical. So this is 2 times 1, 1 times 1.1 times 1 times 1.5, the width of the flow, power 0.65, power 0.512, power 0.43 into y1 is 3.5 power 0.35. It comes out to be exactly 3.33 meters. So we are done with the discussion today. If there is any doubt, please feel free to ask me. Someone had actually asked me about assignment number 5, last question. We solved a very similar equation here, a similar problem here. Apart from that I believe that I made justice to the method of statistics, although it itself should ideally take 3 to 4 lectures of 1 hour each, but I try to explain it in the fastest way possible. Any doubt? Is there any doubt from whatever I discussed today?
Okay, I believe there is no doubt. I shall then stop sharing it and say goodbye for today. We will meet again the next week with new problems regarding the river training, and in the last uh, in the last weekly live session we will sum it up with the important equations to be utilized for this course. Thanks for joining. Stop recording.